Welcome back to this next video series in our Up and Running with the Passive House Planning Package PHPP version 9.7 IP course. I'm Ed May, glad to have you back with us. In this session, we're going to turn our attention finally towards some of the building systems. We're mostly done with the envelope of the building, and so it is finally time for us to start talking about building systems. In particular, in this next series of videos, I want to take some time and talk through the fresh air ventilation system in our building and talk about how we're going to model that appropriately in our PHPP. So let's jump right in. We have talked an awful lot in this class about how the PHPP approaches the question of annual energy modeling. We've looked quite a bit in depth at things like transmission losses, and then more recently, things like solar gains. And of course, we've put that all in the context of this sort of headline equation when it comes to calculating the energy demand over some time period. We said whatever the time period in question is that you're interested in, you can calculate the total heating energy demand and similarly cooling energy demand using an equation just like the one here. We might start by calculating all of our transmission losses over that time period, whether it's a winter or a month or a week or a summer or a whole year, whatever the time period in question is that you're interested in. We might then calculate all of the ventilation losses over that same time period. We would then calculate all of the solar gains and all of the internal gains, and we would find the difference between those losses and those gains. And that would be the method that the PHPP is using to calculate the winter or time period heating energy demand for your building. Now, of course, we've looked at several different pieces of this equation as we've gone through. We've looked in a lot of depth at the annual or the winter period transmission heat losses, the Q sub T. That part of the equation is pretty well done as far as PHPP is concerned. We've entered all of our areas, we've entered all of our U values, we've entered all of our climate data, we've talked about all of our exposure factors, we've entered all of our thermal bridges, all of our window U values. All that is in the PHPP at this point. The PHPP can now go off and calculate those transmission losses for whatever time period you're interested in. Now, as of the last series of videos, our series on the windows and shading, the PHPP can also now go off and do all of the solar gain calculations. So the PHPP knows everything it needs to know now in terms of window areas, orientations, shading factors, climate information, all of the bits and pieces that the PHPP might want to know in order to calculate those solar gains. Those are now also embedded in the PHPP. So for whatever time period you're interested in, the PHPP can go off and calculate those solar gains. So that's fantastic. So now that those are done, let's turn our attention to the next piece of the puzzle here. Let's talk about ventilation losses. How is the PHPP going to calculate this Q sub V, the annual or winter period ventilation losses for our building? Well, it's going to use a relatively straightforward equation. The way to think about how the PHPP is working is to imagine it using this equation right here. In order to calculate the ventilation losses over whatever period you're interested in, you're going to take the volume of your building, in particular something called the V sub V, the ventilated volume. We'll come back and talk about what that is. Multiply it by something called N sub V. So that's a little weird. We'll talk about that. Multiply all of that by something called C air, another kind of weird term. And then lastly, the big G of the winter period. Well, okay, there's some weird terms there. It's not a difficult equation, it's just multiplication. You just multiply one thing by the next thing by the next thing by the next thing. But what are these things? Well, let's talk about it one step at a time. Let's take the easy ones first, because some of these, while they have funny names, are actually quite straightforward. So first of all, the V sub V. That's going to be the ventilated volume of the building. It's the volume of the building, and that's going to be expressed in a cubic foot in the IP version of the PHPP. We'll talk about exactly how to calculate that, but it's basically just the volume of the building. Okay, so fine. Hold off on NV for a second. We'll come back and talk about that in a minute, but let's take the other easy ones here. What about sea air? What does that mean? What is that? Well, that term sea air in the PHPP is used to refer to the volumetric specific heat capacity of air at standard pressure, and that is a constant. That's a number that's known. It's a property of air. Um, and for our purposes in the PHPP, we can use the value 0.018 BTUs per cubic foot degree Fahrenheit. If you prefer in metric, 0.33 watt hours cubic meter degree Kelvin. Now, don't worry too much about the derivation of that. It's not that important. Some nerd worked that out at some point, and we can just use that number. It's just a property of air. Right, we're interested in heat loss as a function of air flow, and so we kind of need to know how much energy we can put into air and how much energy air can transmit and move around. And so we use that sea air, but again, it's just a property of air. We don't need to worry much about it at all. We're just going to use that constant value and just plug that into our equation. And then lastly, the big G of the winter period, or the period under analysis, and that is just our climate data. We've seen that variable before. We've used that variable when calculating transmission losses for all of our different surfaces. The big G of the period is just the heating degree hours of the analysis period. In our case here, that's going to be expressed in kilo Fahrenheit hours per period. So whatever the period is that you're analyzing, a month, a week, a year, a summer, a winter, etc. In our case, we're mostly interested in the winter period when calculating heating energy demand for obvious reasons. So those are relatively straightforward. We have the volume, we have this constant, 0.018 BTUs cubic foot degree Fahrenheit, and then we have the big G, the winter period, big G. Well, that's just climate data. Right? So that's already been entered as part of our work here on the PHPP. So fine, so those are pretty straightforward, I hope. We'll come back and talk about the volume. There's some nuance to that, but not much. The others are straightforward. But what about the weird one? What about that N sub V? What the heck does that refer to? Well, the N sub V is described in the PHPP as the so-called energetically effective air change rate. And that's a mouthful, but break it down into pieces. First of all, an air change rate, an ACH. So anytime in the PHPP, when it comes to ventilation, you see the letter N used as a variable name, the N refers to an air change rate, an ACH. So we're going to see a lot of different N's as we go through the equations here, and they all refer to an air change rate. So N is used as the notation for ACH, for air change rates, when it comes to the PHPP. Air change rate, relatively straightforward, right? It's a volumetric air exchange rate. How many times per hour is all of the air in a space exchanged for new air? Once an hour? Twice an hour? 1 ACH? 2 ACH? Or 0.5 ACH? Once every 2 hours. Right? So you can sort of express air exchange using that ACH. So okay, fine, it's an ACH. So N's are always ACHs. But what about the energetically effective part? What the heck does that describe? What does that indicate here? Well, what it's trying to tell us is, listen, there's going to be a bunch of air moving in and out of your building. What we're interested in is the air moving in and out of your building, which causes some energy transfer. So we're interested in the energetically effective air exchange rate. We're interested in that air exchange which causes heat transfer of some form or another. Okay, so how do we calculate that? What is the N sub V? How do we calculate that? Well, it's made up of two pieces. So there's two different ACHs that get added together to yield this N sub V. So the N sub V is defined in the PHPP as the sum, or the total, of the ACH through the envelope, all of the air leakage through the envelope of the building at normal atmospheric pressure, about 4 pascals roughly, plus the unrecovered airflow through the fresh air ventilation system. And in most passive house buildings, that's going to be an HRV or an ERV, fresh air ventilation system, although it does not have to. In many climates, that is not necessary. But in certainly places like New York, that's going to be the typical scenario for our passive house buildings. So we have two different air exchanges to concern ourselves with. First of all, we have the air infiltration, ACH, the air that leaks through the envelope of the building. And we have some air coming in and out through our ventilation system. And we're interested in both of those, and we're going to add those up. We're going to sum those up in order to yield our N sub V, our energetically effective air change rate. Okay, well, let's take those one at a time. Let's start with the air infiltration, ACH, the air leakage through the envelope at normal pressure. How are we going to calculate that value? Well, we're going to calculate that value using this equation right here. Now, we don't need to worry too much about this at all. Again, we don't really want to concern ourselves with where this comes from. And while it's kind of ugly looking, E times N50 times VN50 over VV, it's actually quite straightforward. Made of three pieces. We have E, which is in the PHPP, a wind screening factor, some number between 0 and 1, representing how shielded or how screened our building is. And we'll look at what those values might be and how we figure out what those values are. Then we have the N50. Well, that's just the tested air change rate of your building at 50 pascals. Remember, for passive house buildings, for certification, we have to test our buildings using a blower door test. And that test is executed at a standard pressure differential of 50 pascals. And so we're going to get this number, this N50, when we build our passive house building. So that N50 comes from the blower door test. And then lastly, all that stuff with the V's, well, those are our volumes. Wait, are volumes plural? How can a building have more than one volume? That doesn't really make much sense. And you are absolutely correct. It doesn't make any sense whatsoever. And yet, it is the rules. The way that the rules are written and the way that the PHPP is built is that we have to input two different reference volumes for the same building. I know. First of all, we have the VN50. This is the actual net interior volume of the building. According to EN 13829, it is the internal visible air. The internal volume is the volume of air inside the measured building or whatever part that we're concerned with. So we're going to calculate that volume to a high level of specificity based on the actual ceiling heights. There is some nuance there. Don't worry about furniture. Don't worry about cabinets, all that kind of stuff, right? So we don't worry about that, but it is all the visible air inside of a space. Now we have another reference volume, though, which is the ventilated volume. This can be thought of maybe in ASHRAE terms. I think they refer to a similar concept as the breathable air zone. This is the air down where people are. So you might have a 30-foot high space, but when it comes to providing fresh air ventilation for people's comfort and health, we're most only concerned with the air down where human beings are. So we're going to use these different reference volumes in different places when it comes to the calculation and evaluation and design of our buildings. In particular, we're going to use that VN50 when it comes to doing things like testing the building's airtightness during the blower door test. But when we're designing our ventilation system to ensure that we have healthy and comfortable interior air, well, maybe we would use the V sub V, the ventilated volume, as the reference for those purposes. So we actually have two different reference volumes that are used in different places in different ways in the PHPP. I know, it's silly to have multiple reference volumes of the same building, but such is the way of it. So we have two different volumes here that we need to enter. Note also that the ventilated volume is defined as the TFA of the building, for PHPP, is defined as the TFA of the building, the treated floor area, times 2.5 meters, or in IP units, 8.2 feet. So that's a standard value for residential. However, for non-residential buildings, the ventilated volume will equal the VN50. So the VN50 and the VV are going to be the same when it comes to non-residential buildings. It's only in residential buildings that we have this sort of nuance there, where we are calculating the V sub V. Now, where do these volumes come from? Well, there's no magic to it. Again, just like everything we've seen in this course, you have to figure out a method that works well for you based on the software that you like and the workflows that you enjoy or the workflows that you prefer. For a lot of the projects that we work on, I can definitely say that we use 3D models in order to determine almost all of these types of reference information, or this type of reference information. In particular, when it comes to doing things like the VN50, where you have to figure out the interior space shape of, oftentimes quite funny shaped buildings. It can be quite challenging unless you're doing something like a 3D model. This is a simplified 3D model of our little example building here. And if we were working on this project in the real world, if this was a project we were really doing for a client, we would almost certainly be building out a 3D model of this form. And then when it comes to calculating the volume, we might actually draw the interior space shape, in particular when it comes to like double height spaces and areas around stairs and et cetera, et cetera. It's often, in my opinion, much easier to actually just build out the interior spaces, draw them out, and then just let the computer do all the counting. You can see here this in an application known as SketchUp, a 3D modeling application, which allows you to do simple planar surface modeling, and that tool is able to calculate those volumes relatively easily, relatively straightforwardly. And so that's one method that you could certainly use. Now, of course, there are other methods if you prefer Revit or Rhino. If you prefer Bluebeam, if you work in PDF, if you want to just do it pencil and paper, somehow or another, you just need to work out the total volume of the building. It's much like the TFA. The PHPP doesn't really care how you come up with that number. You just come up with that number and input that number, and then that's the value that it accepts and goes on with. There is no in-depth sort of detailed worksheet for calculating this inside of the PHPP. So we're left to sort of come up with whatever technique works best for us. So okay, so we have our volumes. So those are pretty straightforward, I think. It's complicated, it's weird that there's two of them, but okay, fine, whatever. Then we have the N50. So we've said already the N50 comes from your blower door test. Right, the blower door test, one of the required steps in any passive house design. It's the way that we ensure and the way that we test the actual airtightness of our passive house buildings. And you can see here a sample test report from one of our projects from just a few months ago. And notice there that the air changes at 50 pascals, the N50. In this case, is being reported out at 0.52, so below that passive house new construction target of 0.6 air changes per hour. So whatever your number is, you're going to input there in the PHPP. So the N50, just an air exchange rate. Again, but the important thing there is that it's tested at 50 pascals, thus the 50 after that N, right? N subscript 50, indicating that that's the air change rate at 50 pascals. So okay, so we were going to input all of that information in order to calculate the air infiltration air exchange, the ACH, at normal pressure. That's fine, all right? So we're just going to input all that information. But then we also have to input all sorts of information about the ventilation system itself in order to calculate a total system air change rate, a total system efficiency, and then figure out the so-called unrecovered airflow through that ventilation system. For our purposes here, if we're trying to calculate heat loss or energy loss, what we're interested in is the unrecovered airflow through that system, the unrecovered energy that flows through that fresh air ventilation system. So how are we going to calculate that? Well, what we're going to first do is we're first going to figure out the NV of the system. Remember, N in all of these notations refers to an air change rate. So the first thing we have to do is we figure out the average air change rate of your ventilation system. So depending on the size of your building and the configuration, what is the air change rate? How much air is moving through your fresh air ventilation system, your HRV or ERV? And then, what is the heat recovery efficiency of your ventilation system? Notice here 1 minus the heat recovery efficiency, that A to HR, and that gives us the unrecovered air. So we have two pieces of our equation there. The average period air change rate of your ventilation system. So again, over whatever time period you're assessing, we figure out the average ACH of your ventilation system. And then we figure out the actual heat recovery effectiveness of the entire ventilation system, both the ventilation unit and any associated or extra heat losses due to the ducting or other components that are part of that system, and all of that becomes part of the total heat recovery effectiveness. And those things get combined in just the manner we show here in order to calculate that ventilation system air change rate. That then just gets added to the ACH due to air infiltration or air leakage through the envelope in order to yield us that NV for the winter period. So a lot of things to put in. The math is not that complicated. It's just multiplication, maybe some subtraction here and there. But we just have to collect a bunch of pieces and then enter them into the PHPP so that it can do all of this calculation. Now there's one other piece here that we should talk about before we turn our attention back to the actual PHPP and start to model these things, and that is, what about the summertime? So everything that I just described to you is exactly how the PHPP is going to calculate the total ventilation losses for the winter period, and it's almost how the PHPP is going to calculate the ventilation losses for the summer period, except that in the summertime, we have the option, we have the opportunity of some extra airflow. So let's talk about what that extra airflow might be when it comes to summer ventilation. Now we should note here that PHI, Passive House Institute, recommends that our effective summer ventilation flow rates should be roughly about 50% higher than our winter ventilation flow rates. So we're going to design our HRV or ERV system, and then we're going to say, what's its operation in winter look like? And then what PHI says is, that's great. In the summertime, your flow rates should be about 50% higher. And that's to ensure hygienic conditions and also to help lower our cooling energy demand. Well, that can be kind of challenging. The PHPP and PHI allows us to specify one of 3 different types of summer ventilation in order to goose the system flow rates, in order to increase our system flow rates, or maybe a combination. We can, of course, have some sort of like boost mode on our HRV or ERV. This can be challenging to design, though. You have to design your ductwork and your system configuration to accommodate the summer rates, and then somehow have a control system that like turns it down in the wintertime. Which isn't impossible, but it's a little bit challenging. I think more common is that we get this extra ventilation through either a dedicated extract air system or, more commonly, through windows. So one of the easiest ways to increase the ventilation flow rates, the amount of air exchange in your buildings in the summertime when it's pleasant out, is to open the windows. And so within the PHPP, of course, we're going to have the ability to model this additional ventilation air exchange due to window operation. But of course, that's not the only way. There are times that we might want to use things like HRVs or ERVs or extract air fans, and so we have the ability to model all of those things. Now, one thing to note about the HRV or ERV systems is that in certain configurations, it may be true that the heat recovery of those types of ventilation systems might actually be working against us in certain circumstances. Those circumstances are not super common, but they might be. For instance, if we had let's say that we have a very, very glazed, highly glazed building, and we have significant solar radiation during the day, and so the inside of the building becomes quite warm due to that solar radiation. And then we're in a climate or a time of the year where it cools off at night. And so we might be in this funny situation where it's actually warmer inside of our building than it is outside. And of course, the way the heat recovery system is designed to work is to keep that heat in the building. That's how it's working all winter long, and we like it that way. But in certain times of the summer, in particular, that can actually sort of work against summer or thermal comfort and energy performance. And so, in those cases, we might want what's known as a summer bypass mode, where we can just take that nice cool outdoor air and dump it right into our building. We can take that overheated interior air and just take it right out of the building, skip around that heat recovery core altogether. And certain ERVs and HRVs are configured with exactly this type of mechanism. And so if that is the case, then we're able to model that appropriately in the PHPP. Note, of course, that in certain circumstances, in certain climates, taking outdoor air at night and just bringing it right into your building might actually cause more discomfort if you're in a humid climate where it might be cool out, but maybe it's super humid, and just bringing all that moist air into the building might actually increase discomfort. And so, it's not the case that this is super useful all year round in all climates, but it can be useful at certain times of the year and in certain climates. And so having it as an option is useful to be sure. And so most of the systems that we're installing nowadays have this as an option, and obviously a sort of controls strategy and mechanism to turn it on when it's useful and then not utilize it when it's not useful. And of course, as we've already talked about, we're going to have the opportunity to model the extra airflow from our windows. Now, this is a really complicated subject. We could have a whole class on airflow and CFD analysis in windows. Super fascinating, interesting subject to be sure. We're going to have a simplified methodology built into the PHPP, which is going to allow us to model air exchange through our windows. So that's going to be really, really helpful for those of us who aren't interested in getting PhDs in computational fluid dynamics modeling and just want to be able to quickly model the effectiveness of a window. So there's a useful shorthand kind of simplified calculator built into the PHPP that's going to allow us to model our windows or window groups and try and assess the effective air exchange as a result of those operable windows. And that, of course, is all going to get built into our summertime ventilation. We have the opportunity to model those during the daytime and during the nighttime. Obviously, you're probably going to have different opening schedules and opening sizes at night and during the day, depending on security and noise and whatever else. And so obviously all of that can get sort of taken into account when we model the operable window ventilation in our PHPP. Okay, so as we turn our attention back to the PHPP, we're going to first take a look at air leakage. Remember, to calculate the ACH of air leakage through the envelope, we're first going to need to figure out our volumes. Then we need to figure out our tested ACH at 50 pascals. We need to figure out our exposure class. So all of that's going to need to go into the PHPP. Then we'll need to talk about the fresh air ventilation system. We'll need to model the system in such a fashion that we can determine the average period ACH of the system itself, the air exchange of the fresh air ventilation system, the ERV or HRV. And then also calculate the heat recovery effectiveness of that system. So we're going to need to enter in a whole bunch of information about the various components of the fresh air ventilation system. And then we'll add in any extra airflow for that summer period. So if we do have any extra airflow that we want to model in for operable windows or summer bypass systems, HRVs, ERVs in the summer period, etc., that's all going to get modeled in to the PHPP as well. So 3 different sections here that we want to jump into as we get into fresh air ventilation. An awful lot to take a look at, but we will move through it one piece at a time. So let's break this video here, and when we come back in the next section, we will take a look at fresh air ventilation systems and air leakage in the PHPP. We'll turn our attention back to the PHPP and start doing some modeling.